Chapter 4. Hawking Radiation as the Cosmic Microwave Background. In 1965, Arno Penzias and Robert Wilson found a pile of poop on their horn antenna. The two engineers worked for Bell Labs as radio astronomers and were troubleshooting a constant hiss in their data. They found pigeons nesting inside the antenna and immediately removed the birds and their droppings, but the interference remained. Soon after, they learned it matched predictions for what is now known as the cosmic microwave background radiation. The residual radiation they measured had a temperature of approximately 3.5 plus or minus 1 Kelvin, a result that soon caught the attention of nearby physicists at Princeton, who had been theorizing just such a phenomena. The signal aligned with earlier predictions of residual heat from the early universe. Ralph Alpher and Robert Herman predicted a cosmic background temperature of 5 Kelvin in 1948, later revising it to 28 Kelvin in 1950. Around the same time, George Gamow estimated 50 Kelvin, later refining his numbers to 7 Kelvin in 1953, and 6 Kelvin by 1956. Robert Dick, also exploring relic radiation in the 1940s and 1950s, proposed values ranging from 20 Kelvin to 45 Kelvin. While the CMB is typically touted as one of the great accomplishments of lambda CDM, the interpretation includes questionable physics and a shaky foundation. A 2025 study from the University of Bonn recalculated the contribution of early massive elliptical galaxies in the background. The study found that these large galaxies could account for at least 1.4% of the CMB. Given that variations in the CMB are only a few hundred microkelvin, even a small contamination from galactic foregrounds could significantly distort the current narrative. The official explanation for the CMB typically goes as follows.
About 380,000 years after the Big Bang, the universe was cool enough that hydrogen could form. Because CMB photons are barely affected by hitting hydrogen, the photons travel in straight lines. Cosmologists refer to a surface of last scattering when the CMB photons last hit matter. After that, the universe was too big, so when we map the CMB, we're looking back in time to 380,000 years after the Big Bang, just after the universe was opaque to radiation.
Hawking radiation. The CMB is considered an almost perfect blackbody spectrum, probably the most perfect blackbody known to man. Blackbody radiation has a very recognizable pattern because it emits 100% of the radiation that it absorbs. Classically, black holes were thought to absorb all radiation they encountered, but that changed in 1974 after Stephen Hawking showed that black holes are not perfectly black. Instead, Hawking showed that black holes emit thermal radiation due to quantum effects near the event horizon. There is a bit of hand-waving around the subject of Hawking radiation. Most literature describes the mechanism as the annihilation of virtual particle pairs, and some sources attribute Hawking radiation to the Unruh effect, which is a thermal radiation bath that is detectable for observers in accelerated reference frames. Regardless of the physical mechanism involved, the proposal here is that the geometry discussed in the previous chapters give rise to measurable Hawking radiation. Very near the horizon, the geometry of our metric is Schwarzschild-like, with the redshift z approaching infinity. The emitted temperature of the radiation is very cold, but the extreme geometry is just enough to blue shift it to the 2.725 Kelvin observed in the CMB. Imagine an observer looking at a star that is both deep inside a gravitational well and at a great distance within that well. Light from a star never reaches the observer because it is too far redshifted to be observed. From the star's perspective, the geometry is reversed, and there is an enormous blue shift. Both perspectives exist for all locations in the universe. Metric formulation. The assumed mass profile from Chapter 3 is m of r equals 2 pi kr squared. This implies a constant radial acceleration of a equals 2 pi gk. Define the radius horizon as RH equals c squared divided by 4 pi gk. With a proportionality of 1 over r horizon, the static spherically symmetric line element becomes, for a photon emitted at the r emit and received at the r observed, the frequency shift looks like this. Choosing the observer at the origin gives us this, and when r is much, much less than the horizon, it reduces to the weak field approximation. Reinterpreting the recession velocity as v is around cz leads directly to Hubble's law, or v equals the Hubble constant times r, or 4 pi gk divided by c. With the prescribed mass profile, m of r equals 2 pi kr squared, the total mass is represented by the mass at the horizon equals 2 pi kr squared, where r is the horizon. A vacuum observer would associate the Schwarzschild radius with the same mass. And there's the Schwarzschild equation. The Schwarzschild radius equation. Thus, the horizon radius exactly equals the Schwarzschild radius of the enclosed mass. It's not a black hole. It's a coordinate artifact that arises because of the chosen coordinates. The CMB calculation. From this perspective, quantum physical effects emit Hawking radiation. And here's the equation for Hawking radiation. The temperature equals Planck's constant, or the reduced Planck's constant, times the speed of light cubed, divided by 8 pi g times mass times the Boltzmann constant. We can rewrite this in terms of a horizon radius using the Schwarzschild relation. The equation becomes h bar c divided by 4 pi Boltzmann constant times rs. For the profile discussed above, we have a horizon and an enclosed mass with the associated Schwarzschild radius. And our Schwarzschild radius is the horizon. So we get h bar times the gravitational constant times the k, our coupling constant, divided by c times Boltzmann's constant, which is the other k, kb. Now, using our c squared divided by 4 pi gk, we obtain a temperature of 1.42 times 10 to the negative 30 Kelvin. Very small emitted temperature. For a photon emitted at r emit and received at the origin, it's proportional to 1 divided by r horizon, which gives us the square root of the r horizon divided by the lowercase delta gives us our 1 plus c. So now we can get the received temperature, which is just simply the temperature observed equals the temperature at the horizon, which is our 1.42 times 10 to the negative 30 Kelvin, times the square root of the radius of the horizon divided by that distance from that delta, which is our distance from the emit location. So it's the horizon divided by the emit location. You take the square root of those, and then you multiply that by our emitted temperature, and this gives us the 2.725 Kelvin. So it's blue shifted Hawking radiation. Now that lowercase delta, for us, the emit location is 2 Planck lengths. 2.15 Planck lengths. That's when we use 72 or whatever, the 71,000 meters per second as our Hubble constant. We get this 2.15 Planck lengths from the horizon is where our CMB is emitted. And then it's blue shifted. So a photon, now we're reading again. A photon or Hawking quantum emitted merely 2.15 Planck lengths inside the horizon is blue shifted by the factor of the square root of the horizon divided by the emit location, or the distance from the emit location to the horizon, that delta, to arrive at the origin with a black body temperature of 2.725 Kelvin. This calculation is highly sensitive to the exact near horizon distance, but requires no new parameters beyond K or the horizon. And it's already fixed by the Hubble constant. One of the things that makes it so remarkable is the narrow range of values for our Hubble constant. Tweaking the value of the Hubble constant changes the horizon value, the emitted temperature, and the Z for the emitted location. As the Hubble constant decreases, the horizon distance decreases. The temperature increases and the Z factor decreases. The required Z to produce the 2.725 Kelvin CMB temperature exists in the happy zone of around 72 kilometers per second. There is some room for fine-tuning, but not much. A better understanding on the physical mechanism that leads to the Hawking radiation could help constrain the emission distance from the horizon. So I've got a table here with 50 kilometers per second per megaparsec, 72, and 100. And then the horizon that those equal, the horizon that comes along with that Hubble value, the delta for the emitted Hawking temperature, and the observed, the 1 plus Z for that frame of reference. Justification. Select a comparison surface by the Planck length rule. R divided by 1 plus Z equals the Planck length, where 1 plus Z is the gravitational redshift between the radius R and the origin in the static geometry. 1 plus Z of R equals 1 minus R divided by the horizon. Near the horizon, R equals RH minus delta, with Z is less than delta and much, much less than the horizon. And then these are the equations that follow. Thus, this rule picks out a two-sphere on a Planckian proper distance from the horizon, matching the fixed UV cutoff recovered from the CMB temperature prediction above. And I'm not going to read the CMB anomalies section. That's the end of this chapter. This chapter is very technical, and so it's not that great on the ears, and I don't want to hurt you anymore. I would suggest listening to the commentary on this chapter. But the rest of the chapter does go into the anomalies, but I just provide a brief overview of the anomalies, and so it'd be better as a commentary than just from me reading the equations.